All right, everyone, today we're tackling a really fundamental topic in power electronics. How do we take the AC power from the grid and turn it into the clean, stable DC power that, let's be honest, our entire world runs on? I mean, this is the unsung hero, the crucial bridge connecting massive power plants to the tiny, delicate circuits inside every single gadget you own. So let's kick things off by asking a really basic but super important question. Before we even dream of designing a circuit, we've got to understand the source. Why is it that three-phase AC power is the absolute workhorse for, well, for just about everything big? We're talking heavy industry, data centers, you name it. It really boils down to two key things: efficiency and power quality. Okay, so here's our roadmap for today. We're basically going to walk through the entire engineering journey, from understanding the problem all the way to a verified solution. We'll look at the rectifier itself, figure out component sizing, smooth out the DC, and then make sure our whole design actually works. All right, first things first, let's really pin down the fundamental problem that every single power engineer has to solve. You can almost think of it like trying to translate between two completely different languages. So here's the deal. The power coming out of your wall socket, that's AC, alternating current. It's constantly flipping back and forth. But all our electronics, they need DC, direct current, a nice, smooth, one-way street of electricity. The device that makes this translation possible, that's our rectifier, and that's exactly what we're going to tear apart today. Okay, let's get to the heart of the matter, the three-phase bridge rectifier. It is an incredibly elegant and powerful circuit. But, and this is a big but, it's not perfect. It has some, let's call them quirks, some interesting side effects that we as engineers absolutely have to deal with. So check this out. Look at the waveform of the current being pulled from the grid. Now, you'd think it would be a nice, clean sine wave, right? But nope. What we've got here is this blocky, kind of squarish wave. So why does it look like that? Well, it's because our load is highly inductive, which means it wants a super smooth, flat DC current. And to deliver that, the rectifier has no choice but to gulp current from the grid in these very specific 120-degree blocks. Now, that blocky shape has a huge consequence. If we use a tool called a Fourier analysis to break it down, we find something fascinating. That weird shape is actually made up of the fundamental frequency we want, say 60 Hz, plus a whole bunch of junk frequencies we don't want. We call those harmonics. And in a three-phase system, the main culprits are the fifth and seventh harmonics. You can literally think of them as electrical pollution that our circuit is dumping back onto the grid. So if it creates all this pollution, why do we even use it? Well, this table tells the whole story. Just look at the comparison between a single-phase and a three-phase rectifier. I mean, three-phase is just better across the board. It's more efficient, it's easier on the components. But the real game changer? Take a look at that ripple factor. That tiny number right there, 0.042. That tells us the raw DC coming out of our three-phase rectifier has only about 4% ripple. Now look at the single-phase, a whopping 48%. That is a huge difference. It means we're starting with a DC signal that's already way, way smoother. And that makes our next job, filtering, a whole lot easier. Okay, so we've got our circuit, but hold on. Before we even think about filtering, there's a super critical step. We've got to size our components properly. We need to pick diodes that can actually survive the job without, going up in smoke. For every single diode in this rectifier, there are two numbers you absolutely have to pay attention to. First is the peak inverse voltage, or PIV. That's the max voltage the diode has to block when it's switched off. In our case, that's √3 times the peak line voltage. The second thing is, of course, the current it has to carry when it is on, which happens for 1/3 of the time. Now, when it comes to current, you can't just use the average value. That'll get you in trouble. You have to use the RMS value, the root mean square. And here's why. And this is crucial. Heat. The heat that builds up in a component is all about I squared R losses. It's proportional to the square of the current. The RMS value gives us the true heating effect of that weird blocky current, and that's what keeps our diodes from melting down. All right, we've designed a rectifier that won't blow up. That's a good start. Now for the fun part, the refinement. Our DC is pretty good, but it's not perfect yet. It's time to open up the engineer's toolkit and grab some passive components to filter out that last little bit of AC ripple. Let's get that signal clean. So when it comes to filtering, we've basically got three main tools in our arsenal. We've got the L filter, which is an inductor we put in series with the load. We've got the C filter, a capacitor in parallel. And then, for the best of both worlds, we can combine them into an LC filter.
So, how does an L filter work? Well, an inductor's whole personality is that it hates change in current. It's like a choke. So, when we put it in series, the steady DC current just cruises right through, no problem. But that AC ripple current, the inductor puts up a huge fight and basically blocks it from getting to the load. And this handy formula lets us calculate the exact size of the inductor we need to get the job done.
The C filter, on the other hand, works completely differently. We stick this one in parallel, and it acts like a little energy reservoir. When the voltage from the rectifier is high, the capacitor charges up, storing energy. Then, when the voltage starts to dip down, the capacitor discharges, releasing that stored energy to fill in the valleys. It just smooths everything out. And, you guessed it, just like with the inductor, there is a design formula for this too. We can plug in our load, the ripple frequency, and whatever our target ripple is. Let's say we want it under 5%, and this equation will spit out the exact capacitance we need. But if you want the absolute best performance, you use both. You build an LC filter. Now, this is a really slick design. It basically acts as a voltage divider, but only for the bad stuff, only for the ripple and harmonics. The inductor in series blocks them, and the capacitor in parallel gives them an easy escape route to ground. They never even make it to the load. The result? A beautifully clean DC signal, way better than what L or C could do by themselves. Okay, we've designed our circuit, we've picked our components, we've added our filter. Now we come to the final, and I'd argue the most important step of all, verification. It's the moment of truth. We've done all this math on paper, but does it actually work? This is where we turn to simulation software to test our design in the virtual world before we build anything in the real world. And boom, here's the proof in the pudding. We simulate the entire circuit using a program like PSpice, and just look at the results. The total harmonic distortion, the THD, comes in at about 5.6%. Our design goal was to get under 10%, so mission accomplished. The simulation confirms our design works. But wait, our job still isn't quite done. You see, a good engineer has to think about the bigger system. Remember that electrical pollution, those harmonics we talked about at the beginning? Well, our circuit is the thing creating them, and we have a responsibility to make sure we're not messing up the power grid for everyone else. The solution? You guessed it, another filter. But this one goes on the AC input side, before our rectifier. Its whole job is to trap those harmonic currents and shunt them away so they never escape back onto the grid. Now, there's a huge word of caution here. You have to design this input filter very carefully. Get it wrong, and you could create a resonance with the grid itself. And trust me, that is a recipe for disaster. So, let's boil this all down. What are the big takeaways? 1. For high power, 3-phase is king. 2. Inductive loads mean you're going to have harmonics, period. 3. Safety first. Always calculate your PIV and RMS current to avoid fireworks. 4. Use L, C, or LC filters to get the clean DC you need. And 5, and I can't say this enough, always simulate before you build. Always. And that brings us to a final thought, a little something to chew on. Everything we've talked about today uses passive components, inductors and capacitors. They're dumb, they just do their job. But as our loads get more complex and our electronics get smarter, what about the future? Could we see active, intelligent filtering systems that can adapt in real time? Now that's where things start to get really interesting.